So let's talk a little bit about the 2 to 4 decoder from the book. I have the circuit diagram here, and you'll see it looks kind of messy, and we'll fix that in a minute because you'll see there's a much easier way to accomplish these by going back to the truth table and just laying out the circuit a little bit differently. And I've also fixed the typo that's still in the book. In the top right, I believe in the book it says X not and Y, and of course it's X and Y for the top right gate. Let's first build this in the simulator, and I have built this already, and then I'll show you the dynamic behavior on this and why this is called a 2 to 4 decoder. Okay, here's the circuit that you've seen from the book. In the simulator, of course, it uses the international European rather than American symbols, but you'll get the gist here. So the ampersands, of course, are AND gates, and then there's a little NOT gate right here. We got our two input variables, X and Y, and so we'll treat those inputs as the binary numbers, with X being the most significant bit and Y being the least significant bit. So X of 1 and so Y of 0, for instance, would represent the number 2. And then so we this is why this is called a decoder. We can use these two numbers and decode them so that for each of the 4 possible output lines, exactly one will be actually high and switched on at any given time, with the others being low. And then of course data line 0 will correspond to the number 0, data line 1 will correspond to the number 1, and so on. So we encode, we decode the number to a particular line that is high. You can use this, for instance, to specify a let's say an output line. Let's say we want to set output line 2 to high, then this is what this would represent of all the 4 possible output lines that we have. Let's run this so you can see the dynamic behavior, because then it becomes much clearer. So I'm just going to run the simulation here, and now you see that X is 0 and Y is 0, and therefore the data line number 0 is high. I go X0 and Y1 and representing the number 1. So line number 1 now is high. I toggle that around, X1 and Y0. Now line number 2 is high, and then both bits on number 3 and number 3, line number 3 is high. And that's what a decoder does. A decoder does pretty much the inverse thing of that, and we're going to come back to that. But decoder decodes a number and basically outputs the number or sets that line to high that is represented by that binary number. So, and this is, as you can see here, relatively messy, and there's a easier way to actually represent and build these kind of gates. But before we get there, let's have a look at the truth table. So we will look at the truth table for the decoder. It's actually a relatively simple pattern that you can detect here. These are actually 4 truth tables condensed into one. They all share the same input, X and Y, going through the classical binary sequence 0, 1, 2, 3. Then we have 4 output lines, D0, D1, D2, and D3. And when X and Y are both 0, then D0 is 1, and all others are 0. So only one, as you can see in the pattern, only one output line is active at any given time. And which one it is dependent exactly on the bit pattern of X and Y. So if the bit pattern of X and Y represents the binary number 1, 0, 1, then line D1 is active. Same thing then if X and Y are both 1, for instance, then line D3 is active. So it's a relatively simple pattern, and you will see that it's also actually relatively simple to create this pattern into a very simple circuit that does exactly the same as the somewhat messy thing we've seen before. So let's go back to the simulator, and it all comes down to realizing that we can use the sum of products in this case representation to actually go into the truth table and directly construct our circuits without having to do anything special, and the structure will actually be represented in the circuit exactly. So let's do this. So here I'm back at the simulator, and I'll leave the other circuit in place so that you can indeed see later on that the behavior is exactly the same. And so whenever you build these truth tables, all they do really is combine their input variables to their output, and the first stage may or will almost always combine both variables in their normal and negated form. So what we'll do here then is we'll create basically 4 lines, and we typically run those vertically, that represent both our input variables and their negation. So let's do this here, and let's say, okay, here's our x, and then let's go here and create our y. And so these are our input lines, and let's just run input lines straight down here. So let's just place down our toggles where we need them to be. And then we're going to run those lines straight down the board. Okay, so now we've got this, and let me actually move these two here over one. Okay, and now we can actually add the negated lines. So let's add a negator here, and we're going to put this in the down direction, and put this down right here, and we put another one down right here, and then we make the connection here from here to here, and from, well, actually let's run the connection off of this one here. So and let's also create this line down here for now, and then let's create this off here. Right, so whenever you have these lines crossing and you'll see a dot, that means they're connected, of course. So we're going to run these lines down here as well, right? Which means that now we actually have all 4 of our lines together. Actually, let me again move this a little bit more by just moving this one over to create this a little bit more compact. Okay, so now we have 4 lines. The left 2 represent x and not x, and the other one y and not y. So, and if we look back at the truth table, we can now see that we can directly build our gates as the sum of products, because remember, then we have the sum of products. The output is true when any given of the product terms occurring in the sum are true. So in our particular case, the truth table reflects that relatively nicely, that in the sum of product terms we only have one entry that actually does that. So let's build the first term, because the first term for D3, for instance, here when we want to build that again in this order that you see on the right hand side. So let's start out with D3. So D3 is true when both x and y are true, and none of the other terms fall into them. So let's create an AND gate that we put right here. And oops, and I need to actually turn this thing, because I want it in the horizontal direction like this. Okay, so here's my AND gate, and then I want to build it so that now the output is true whenever X and Y are true. So here's my X line, and I'll take that and just move that over here. And then here's my Y line, and I move this over here. Let me add an output so that we have that available to us, and connect it and actually label it D3. Okay, when we run this now, we will see that this gate here indeed is only high and true when both X and Y are true, because that's how we wire it up, and that's what the first term in our sum of products actually tells us. So we go into the first or into the actually fourth entry into our table, representing the binary input number 3, and we see that, okay, this is the only one that's being true, so I can actually write it like this, and all the other terms have to be false at that time. So now I can go ahead and edit this any further. Let's do D2 then. So D2 then will look like this. So let's add this. And so it's a little hard to put those down in the exact location that you want. Okay, and so this is D2, and if you look at the output line for D2, we'll see that this is true only if X is 1 and Y is 0. So if X is 1, that's pretty simple, right? We take our X here and connect that to the input. But now, if Y has to be 0 for this to be true, which means that not Y has to be 1 to be true. So I just go here into the not Y column and wire that up, and I have my D2. So now I can add my LED, connect it, and I have my label that I attached to it, D2. If I run this now, indeed, this should be true only if X is 1 and Y is 0, right? And of course D3 and all the others down the road should also be 0 as well. So, and now I've got X and Y both as 1. So, and that's how you build this from the truth table. You just go back into the truth table, and you can pick your terms from the sum of product form, and then just wire them up accordingly to your inputs. You see when is your output 1, you look for all the inputs, wire the 1 inputs directly, and you wire the 0 inputs into from their negation. So let's add D1. I think by now you see where this is going. It should be a relatively simple pattern, right? So let's put this down here. So now I've got my D1. That should only be true if X is 0 and Y is 1. So if X is 0, which means here I go to the negated line and wire that up, and then Y on the other hand has to be 1, and then I can add my output and wire that one up, add my label for reference, D1, and running this, we should see that this is, I made a wire, as you can see here, right? So I made a mistake in wiring this up. This should be true only if X is 0 and Y is 1. I wired it up here to the negation. So let's just get rid of, that line and rewire it correctly. So we're going to go here into X, of course, like this. Sorry, no, 0 and 1. So I've got it exactly the other way around. So let me do this one more time. So let me just delete that wire and delete that wire, and then again, now correctly. So D1 must be 1 if Y is 1, which is right here. Hold on, and again, let me undo this. The Y input is down here, so let's X must be 0, so that's this, and Y must be 1, that's this one. Okay, so now we can go ahead and run this, and we should see that this is only true when we have X equal to 0 and Y is equal to 1. Okay, so we've got that, and now we can wire up the last one. And let's do this, and we'll place down our gate, make the connections. This is D0, so that has to be high if both X and Y are 0. So we go to the X negation and the Y negation. So that's not X and not Y. We add our output right here. Wire that one up and add our label here, which is the D0, and we are good to go. And now, indeed, so 0, 0 gives me D0, 0, 1 gives me D1, 1, 0 gives me D2, and 1, 1 gives me D1. So, and if you follow the traces correctly between the left circuit and the right circuit, you will see that they're indeed completely identical, as you can see that they implement the same truth table. But you also see that the structure on the right-hand side is much, much easier to understand and easier to see, because you can directly reconstruct the truth table from the circuit and vice versa. And whenever you typically see circuit diagrams for control units for CPUs, this is what they're going to look like. So you'll always have typically all combinations of input lines available to you, and then you just make this matrix of connections that you will need from the truth table that you just constructed. It's a relatively straightforward process, and as I always mentioned in class, this is not hard, just tedious. Of course, then we have tools to minimize, before we implement the wiring, tools to minimize the truth table. But even after that, we just look at the truth table, make the connections, and it's so simple that a computer can do it, and that's exactly what we have. We have programming languages for these kind of things. Verilog and VHDL are two programming languages that basically take these truth tables and spit out wiring diagrams like that, because it is not hard but tedious. So that should get you, give you enough information to understand many of the circuits that we'll see, and also successfully complete the assignments I'll give you when it comes to actually wiring these circuits up.